Hey everybody, and welcome back to Algebra 2 Online. So the plan for today is to talk about the tangent and cotangent functions. And I'm also going to talk a little bit about the inverse trig graphs. I'm not going to get into inverse trig graphs too much because they're kind of weird and it's kind of more of a pre-calc concept anyways. You'll see it there. But I do want you to at least see them, and there's some important stuff related to inverse functions and specifically the word functions in there. So we'll talk about that in a bit. But to start off, I want to just kind of fill in this table right here. So, if I want to evaluate tangent at like nice angles like this, right, I'm really just thinking of doing the square root of fingers below over square root of fingers above trick, really because it's, sine over cosine is equal to tangent, right? So this is square root of fingers below over 2. This is square root of fingers above over 2. The 2's cancel, and so you get this. So literally, like when I do 0, there's no fingers below, so it kind of tells me right off the bat this is 0. If I go up, to my ring finger, I guess, 1 finger below, 3 above, so it's basically square root of 1 is 1. It's 1 over square root of 3. The nice one, right, for tangent is actually the pi over 4, because it's halfway kind of through the hand, and so you get the same amount of fingers above and below. You're going to get a 1, right? And then you would get root 3 for pi over 3. And then for 90, right, you would get, square root of 4 fingers below divided by none above. And so this thing is undefined, right, on the bottom one. And I'm going to actually do... So it's undefined, but it would sort of be like 2 over 0 is really what it would be like, right? Which we know we can't do because it's, square root of 4 over square root of 0. But that is actually going to be helpful for filling in cotangent, okay? Cotangent, you just take the reciprocal. 1 over 0, that one is going to be undefined. So we'll put undefined there. Flip that around, you get root 3. Flip that around, you get 1, right? And flip root 3 around, you get 1 over root 3. And then the last one, right, it's actually not going to be undefined because... the reason this one undefined is because 0 was on the bottom, but really 0 would be on the top now, and you're going to get 0 there, right? So one of the things to see is that when tangent is 0, cotangent is undefined, and vice versa, when tangent is undefined, cotangent is 0, right? So if you look at this picture, you can kind of figure it out from that stuff, but I'll just kind of tell you right here. This one down here is tangent, right? And this one up here is actually, gotta fix that, cotangent. There we go. And, let me just highlight a few things. Like, notice every time tangent is 0, right, you have a dotted line for cotangent. It's undefined there. When you're at pi over 4, right, which is like halfway right here, you're going to be up at 1. And notice that's the same on cotangent right there. That point is shared because the reciprocal of 1 is 1. And same thing with actually negative. If you do negative pi over 4, then you're going to be at negative 1. And if you're at negative pi over 4, you're at negative 1 still. So that part is shared by both. What else do I want to point out? Notice when, this gets really big, this is getting really, really, really small because it's the reciprocal, right? So as you go up in numbers here, you get like 10, 100, 1,000, blah, blah, blah. If you do 1 over 10, 1 over 100, 1 over 1,000, this should be dropping. And then when it's basically infinity, right, when this gets close to like nearly largest number you can ever possibly think of, this is 0. This is the smallest number you can ever think of. And so there's kind of like an inverse sort of relationship, like this goes up, this comes down, that kind of thing. So that's kind of another pattern to see. But, one of the ways I think students usually remember this is they just sort of see the symmetry here. So tangent is, it's going to go right through the origin, and you just tick off the asymptotes at negative pi over 2 and pi over 2. And cotangent, it's just shifted over and kind of flipped around. Cotangent kind of looks like negative tangent, shifted over. Actually, in fact, I can be explicit with it. Cotangent of x actually equals negative tangent, so that's the flipped upside down part, and then shift it pi over 2. That's actually true. If you graph this, it looks exactly like this, okay? But yeah, the way I'm going to look for graphing for these things, like since it is periodic here, I'm looking for basically just one of these kind of shapes with 2 dotted lines. Same thing here, I'm looking for one of these shapes, 2 dotted lines. I'm going to emulate right over here. So I'm going to go through just a graph of minus 2 tangent, pi x plus pi minus 1. And just like any of these, if there's a multiplier in here, I would factor everything out so you know what b is and you know what the shift is. So we got minus 2 tangent pi over x plus 1 minus 1. Okay. One thing to note here, okay, let me actually go back, sorry. Notice that this graph is periodic not in 2 pi. Negative pi over 2 to pi over 2, or pi over 2 to 3 pi over 2. You're getting a full cycle of the graph in pi, so half of what you're used to. And same thing up here, from 0 to pi, you get a full cotangent. From pi to 2 pi, you get another cotangent graph. So the period for tangent or cotangent is actually just pi over b instead of 2 pi over b, all right? That's like a little difference. And the asymptotes for tangent are just, pre-shift. Let me kind of write that in, pre-shift, right? They're going to be at 0. Asymptotes. I thought we were talking about 0. Sorry, the asymptotes would be at like negative pi over 2, pi over 2, 3 pi over 2, etc., etc., etc. These are just the times where, because tangent is sine over cosine, when cosine equals 0 is when you're going to have asymptotes, right? Because in that fraction, then the bottom is 0. So cosine equals 0 at those kind of increments in the unit circle. So that's when it's going to be, there's going to be an asymptote. Okay, so just like sine, cosine, secant, cosecant, I would start by doing the period. So it's pi over b, but b here is pi. So it's actually got a nice period of 1, okay? So I might actually just do 1 here, and then that's going to be 1/2. That's 0, of course. This is 3/2, and this is 2. So I'm actually going to graph 2 periods just to kind of show you what it would look like if we kind of keep going. And then the midline is normally, the x-axis, but because there's a -1, it means we're going to shift down, and I'm just going to say this is -1. I realize the scale is different, but that's okay. So that's going to be like my midline for this graph. This would normally, affect, it does affect, it does, the vertical stretch by 2 is going to be happening. But my policy sort of, when I first teach these concepts, is don't worry about it too much. You can try and make a steeper, tangent curve. Like what I mean is instead of maybe this curvature, it's kind of like that. It'll sort of pull everything up and down by a factor of 2. So it gets bigger quicker and drops quicker. But it's hard to draw that. I don't really expect you to factor in the 2, to be honest. It's mostly the other things that are going to matter a lot here. So don't worry about the 2. And then the negative is definitely going to matter. And then the only other thing we have to do is the +1 here. So normal tangent, is basically has a y-intercept. The cotangent does not have a y-intercept. Tangent does. So normally I'd be here at this point, and I would kind of go up like that, right? But for this one, right, the +1 means it's going to shift 1. So, there would have been a point here. There would have been a point here, and there would have been a point here. And, you would have had this graph, would have had this graph. But we're shifting everything to the left. To the left one. I looked at this for a second. So +1 in here means we shift to the left one. So this point actually moves here. This point moves here. But if you see what's happening, it's shifting by the period. So it's actually not going to change it, right? This +1 is just kind of superfluous. It doesn't matter at all. Then you just need to remember kind of where the asymptotes are. So the asymptotes for tangent sort of bound. They're kind of sandwich the y-axis. They're to the left and to the right. And so you're going to get an asymptote. Let's see, I'll just do this one. You're going to get an asymptote here too. And then, normally we just put in a curve like this, right? But we have a -1, so instead of being that direction, right, it's going to flip, it's going to come down like this. Like this that would curve up would curve down. So the final graph would look something kind of like this. Just draw something that curves in like that. Draw something that curves in like that. I don't really have a lot of room there, but draw something that curves in like that. So here you can definitely see over a period of it. And in terms of graphing these, as long as you show at least one full cycle of it, you're good. So that is what -2 tangent pi times x + 1 - 1 would be. So cotangent, very similar kind of thing. Really what we're going to just kind of keep in mind is the basic look of them, like this. Now normally where the zeros of tangent happened is where you're going to get asymptotes this time. And so that's, going to kind of dictate part of our answer for us. Another thing to keep in mind is that, because we're talking about reciprocal functions, whenever tangent is big, cotangent is going to be really small. And whenever cotangent's really small, or when tangent's really small, cotangent's really big, right? So 1 over a big number, small number. 1 over a small number, big number. And cotangent is undefined when tangent of x equals 0, right? Period is still pi over b. And the asymptotes are when, that's linked to this, really, when tangent equals 0. It's the same thing. So I'm going to do the same kind of trick. I'm going to do for cotangent. Whoops. Just writing cosine for a second. Take out this pi over 8. And then maybe down here, we want to think, okay, pi over 8 times something is equal to pi over 2, right? It's going to be a negative in there. And so you can just do the same thing. You can just divide pi over 2 by pi over 8, right? And if you do that, right, If you multiply top and bottom now by 8 over pi, you're going to get 4, okay? So that is equal to 4. You can also just, always check these things to make sure you did it right. Pi over 8 times 4, you do 4 over 8 is 2, right? So that's good. Close that up, minus 2. All right. Period is just going to be pi over b. b is pi over 8. So if we simplify that, that would be 8, right? And so let's do the same thing. I think we're going to, as the last problem, I'm going to do maybe 2 cycles. So we'll do 8 there, 16 there. That'll be 4. That'll be 12. That'll be 0, of course. And then the midline is shifted down 2. That's what that number would tell me. So my midline, this would actually be 2 with the same scale. And then we have an amplitude, not an amplitude, sorry, there's no amplitude here. We have a vertical stretch of 4. I'm just too stuck in cosine right now. We have a vertical stretch of 4. But again, I'm not really looking for that. I mean, it's going to change the curvature of your cosine, or your cotangent, I'm so sorry. But it is not something I'm really assessing that you can show accurately in the picture. It's just too fine of a detail to see. I mean, you can always plug in numbers and get points that way and really get a good graph, but we're just trying to make a rough sketch here. So then there's a shift to the right 4, okay? And so now it just comes down to, knowing the general shape. So, normally you have one full period kind of between 0 and pi. Now we're doing 0 to 8. But normally we have like asymptote there, 0, and it just keeps going from there. So we would normally have an asymptote here, but we shift it to the right 4. And so we're not getting an asymptote on the y-axis, we're getting one there. The other one would have normally been here, but we shift that to the right 4, and so we're there, right? And then there would have been another one here, but that's shifted over, right? So we can't really see that. And same kind of thing, we're missing, we can't really see one there. But there would have been a 0 here, right? And it would have kind of looked like this. But that 0 is shifted over. So that 0, I almost messed up. So we're down 2, don't forget. So we're going to have a 0 down there, actually. And then really, just general shape. I mean, the 4 is going to make it steeper, but I'm not really looking for that kind of thing. There would be another 0 there, and then, we're going to kind of be able to, I'm not doing a very good job with my curves. There would be another 0 there, and it would go up and kind of be off the page over there. But we've got plenty of it here. So that would be cotangent. That's like the normal direction for cotangent. You really want to make sure you just know the general shapes of tangent and cotangent. That will be really helpful for graphing these. All right. The last thing I want to talk about is inverse trig functions a little bit here. Turns out they're kind of more annoying than we might think. It seems very reasonable that sine inverse of sine of x would be equal to x. But that is not the case, okay? And it's actually pretty easy to see. If you think about, sine looks kind of like this, right? This function, it is, a perfectly well-defined function. It passes the vertical line test, right? But it's a horrible function with the horizontal line test. If you think about horizontal lines, drawn over here, all over, it fails the horizontal line test, really horribly. This thing, right, should then not have a well-defined inverse function, which it definitely does not, okay? Turns out that there's a portion that's really good. There's lots of portions, actually, that are really good. And we kind of, just like square root, we just defined where the inverse sine function is. And I will talk about that here in a second. But just to kind of show you, right, that this is not going to be true, you could always just plug in numbers, right? If you do sine, like, if you test it with, like, make sure your calculator's in degrees, okay? If you do sine inverse of sine of 0, right, you're going to get 0. Perfectly good. It's kind of what you would expect. If you did sine inverse of sine of 30, okay, you would get 30. That's perfectly fine. If you do sine inverse sine of 90, you get 90. Like, so far, everything here makes sense. If you do sine inverse of sine of 180, you get something really weird. You get 0. If this was a well-defined inverse, then sine inverse of sine would truly just cancel all things, and x would be equal to x, right? It would be fine. But that's not what's happening. Sine inverse of sine of 180, sine of 180 is perfectly well-defined, right? That's a fine thing. But the inverse function is not giving you 180 back out. Something is happening, right? And just to show you another one, if you do sine inverse sine of 234, you get negative 54, okay? And so, what is happening here? Okay, something weird. Sine inverse is just, sine inverse fails sine fails the horizontal line test. So inverse sine function should not be well-defined. That's what that test is testing for. So question becomes, like, what is the graph of inverse sine and what's going on here? So this is basically the picture that is happening. All right, so this blue graph is sine of x, okay? Or sorry, not blue, purple. This is supposed to be a straight line, y equals x, okay? We know that the inverse is just the reflection of this thing across that line y equals x, right? Something we saw way back in this course. Turns out if you flip everything over, right, it basically would look like a sine graph kind of going up, I guess, the y-axis like that. And what we've done is we've basically, because, if you have a wave function going this way, it's going to fail the vertical line test, right? Horribly, right? All these different things are going to fail. Vertical line test now. What we did is we basically just took a portion of this graph as the inverse. It's the same thing we did with square root, okay? So basically what this ends up looking like is you get this kind of shape, and I have a better example of it. So I fixed it a little bit. That's basically what it looks like. I have an actual graph on the next page, but what we actually just did is we took a region of sine of x. We took specifically this region, which kind of makes sense because it's the part like right around the smallest numbers, right? And if you just flip that over the line y equals x right here, you get, this kind of shape. And so that becomes actually what the entire graph of sine inverse of x is. And they did the same thing with cosine too. So this is actual graphs. This right here is exactly what you get when you type in sine inverse of x, okay? It is just literally that. That is all there is to it. This one is what you get when you type in inverse cosine of x, okay? And this one truly is, with grid lines, I can do it a little bit better. It really is just the reflection of the cosine graph, which I'm trying to map out here. It's the reflection of this cosine graph, roughly, right, over the line y equals x. Most importantly, it's, this red part right here, we just took that as the inverse, and it is specifically the reflection of just a portion of the graph right here. It's a portion of that graph, right? Hopefully you can see the symmetry of the red and the purple there. But like as soon as you would go further, like let's do it in a different color here. So as soon as you would go further, like as soon as you include this, now that part's going to fail the horizontal line test, which means if you included it in the original, if you include it in the function over here, it's going to fail the vertical line test, and hence not be a function. So really we just adopted part of the reflection as the inverse functions for these two. Really just think back to square root, right? This graph flipped on its side should look like that, but we know that we only take this part as square root. That's what square root of x is. It's the exact same story. We're just taking part of the graph as the inverse to keep it well defined. We're just restricting the domain, basically. And this one, okay, this is actually what inverse tangent looks like. And you'll notice actually it looks like a perfectly well-defined thing. And that's because if you think of tangent, right, I can kind of color code this actually a little bit. So this will make some sense here in a second. All right. If I was to flip over y equals x, this blue horizontal vertical asymptote, right, is actually going to act as an upper bound for the function up here. And this vertical asymptote, if you flip it over, it acts as a lower bound on the function down there. And so that's actually where its kind of flattening effect on top and bottom comes in. Like this graph actually, the inverse tangent, has horizontal asymptotes, which is kind of weird. And so, yeah, so this red one is tangent. If you flip around, you get inverse tangent, which is actually really well defined. These are kind of like the three main things I just want you to know. Sine inverse has only the domain -1 to 1, okay? And the range is also restricted from -π/2 to π/2. You can see all that here. It's kind of just defined in that little rectangle right there, right? That's it. That's the whole graph. No arrows or anything like that. Cos inverse has domain -1 to 1 and the range 0 to π. Again, you can see that down here, this red graph. But inverse tangent is defined from -infinity to infinity, and the range is -π/2 to π/2. That part's restricted, right? But yeah, these were the vertical asymptotes, which, you know, restricted the x's for tangent. And so in a sense, they will restrict the outputs, the range values for inverse tangent, sorry. So I wanted to just show you like one quick example that involves inverse sine. So I'm going to start off with kind of going back to our unit circle and the all students take calc thing. -√2/2, right? For, we're talking about inverse sine, so think sine, right? This is like an output, right, that we're plugging in for sine. So to have a negative output for sine means we can't be in that quadrant or that quadrant. So we have to be in here or in here, right? But inverse sine is only defined from, I'm sorry, not defined. Inverse sine outputs only between -π/2 and π/2. And so what that is, right, is this is -π/2, right? And then this up here, right, is π/2. And so it actually forces us to not be in that quadrant, right? Because we knew we're not in that, we knew we're not in that. We can't go past this value, so I have to be in that quadrant, right? So then the question is, when do I get like the √2/2 thing? And so that would be like a 45 situation. So I'm basically have to be at, right, -π/4, right? Because inverse sine functions output angles, right? That's why you see angle, 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 right? But that's it. That's kind of like a weird issue that can happen with inverse sine function. You have to actually give me -π/4 on that one. None of the other things work. You don't get two answers or anything weird like that. So I do want you to know this kind of thing. We will see some of that. That's kind of it for graphs of tangent and cotangent.